Hi everyone. We're just going to go over a little bit of radioactive decay as a little separate part of the physics class. You guys are currently taking physics, I believe you said, so you're probably going to go into a lot more in-depth on this topic and the other physics topic that we cover for this week. But it's worthwhile to go through it anyways, so I'll just start. One really important thing to take home is that radioactive decay is a random process. It doesn't You can't look at a single individual atom and know when it's going to decay. Even if you know the isotope, you know its half-life. It's sort of a law of large numbers is that the only way that half-lives exist is when you have tens of thousands, hundreds of thousands of atoms. Fortunately, in most real-world scenarios, this is exactly what you have. So the half-life does hold, and that's why it's so important and so readily used. But it is technically a random event. Um, so you hear about logarithmic decay. That means that you have a half-life. It's the time that it takes for 50% of the atoms to decay, but that does not mean that another half-life will have the remaining 50% decay. That means that it'll be another half and another half and another half, and that's what leads us to this sort of logarithmic curve that you see here. It looks like after 10 half-lives, it goes down to nothing remaining. We use 10 half-lives as sort of a rule of thumb to say that after 10 half-lives, most real world sources will be down to zero, or at least most medical sources. This is not always the case though. If you switch to an actual semi-log graph, you'll notice that in this graph, the y-axis is actually logarithmic. The x-axis is still linear. But when you plot on a semi-log paper, your decay curve turns into a straight line. So that's why a lot of decay calculations before the dawn of the computer age really relied on this semi-log paper. And you can see that 10 half-lives brings you down to about 0.1% of your initial activity. So that's still, that's a very small, it's a little over 1,000th of what you originally started with. So if you had a lot of activity to begin with, 1,000th of that activity could still be a pretty substantial source. So that 10 half-lives is not set in stone. It's just kind of a little rule of thumb, but there's lots of situations where it does not hold. One instance of actually a historical case where there was an error due to a mix-up of semi-log versus linear graph paper is back in the 1970s at Riverside Hospital. They had a physicist that was taking over for another physicist, and he was in charge of calibrating their cobalt teletherapy machine. Now, he did this on linear paper, whereas the previous physicist had been doing it on semi-log paper. So he just continued these curves, continued them. Unfortunately, over time, this error led to showing that the machine was decaying much, much faster than it actually was. So there was no checks with secondary instrumentation to verify this output. So for 2 whole years, the calculations were the sole thing that were deciding most of these patients' prescriptions. And in that 2 years, there were 426 patients that received anywhere from a little overexposure to a lot of overexposure. The patients towards the 1976 end of this curve definitely got more than the ones in the beginning, but there were definitely some pretty negative effects that happened from this. I read a paper as recent as 2014 where there was still some legal fallout from this. It's a difficult situation because you have very sick patients that are getting this therapy. So then there's the whole question of if the overexposures were the cause of the patient's problems or their underlying cancer, and that's something that's difficult to figure out. There's really no way you can ever know for certain. But ultimately, yeah, the fallout from this situation is still going on. And yeah, it's one of the most prominent cases in terms of failures of cobalt teletherapy, which was seen as a very reliable therapy just because of that known decay of cobalt over time. But it initiated a lot of changes, a lot more regulations, as all sort of previous accidents tend to do. But it really tried to make sure that these the calibrations of machines were happening more regularly. You can't just calculate on paper. You actually have to have measurements of the radiation output. And that's it's the same for linear accelerators. There's very extensive QA programs that make sure that these measurements are taken on instrumentation as well as theoretically. at least for cobalt teletherapy. So there's a value known as the decay constant. The variable is, it's a lambda sign. So the decay constant is simply the natural log of 2 over the half-life of the isotope. We get into natural logs because of that logarithmic decay. That's how you can calculate activity at a certain time point, or just if you're trying to figure out how long it takes for a certain source to decay to a certain activity that you may have in mind. So you can use that with the factor of lambda, which is essentially based off of the half-life of the isotope. So we'll get into that a little bit more here. So the mean life, actually, before we jump into the actual decay equation, just a quick discussion of the mean life. The mean life is simply 1 over lambda. So this, if you have a certain number of atoms, the mean life is pretty much how long will be the average of the life of all those atoms. And it turns out that it's a little bit more than 1 half-life. If you think about it, half of those atoms being gone in 1 half-life means that that's half of them having been gone, and then the other half will decay much slower because half of that half, and then half of that remaining half, and it's that logarithmic decay. But essentially, because of that first half decaying right in the first half-life, most of the atoms will decay shortly after that, or will have decayed shortly after that, if you're looking at the totality of the atoms in that source. So I know that's a little bit of a confusing description, but ultimately it's useful for calculating dose. Because if you think about dose from something like a nuclear medicine procedure, it really comes down to the number of atoms decaying in a certain tissue. That is dose. All those little individual decays adding up to a biological effect, and that's we're talking about tens of thousands, hundreds of thousands, millions of decays, but they are what are actually causing that dose. So a lot of times you'll see in certain dosimetry functions there that you use this mean life as a means of getting accurate decay information and dose information. Activity is something that you hear all the time when you're talking about radioactive materials. It's a very important concept. It's kind of a strange concept though, because when you hear activity, you hear a high activity, you think of it's a physically large size, but that's not always the case, because activity is simply measuring the rate of change. It's not actually measuring the size of a source. It's measuring how quickly a source changes. So something that has a long half-life, if it still has a high activity, that means that there must be many, many, many atoms of that isotope there, because something like I-129, iodine-129 has a multi-billion year half-life. So if you have decays happening every second, you must have a lot of iodine-129 atoms there, because most of them are not going to decay for a billion years. But the ones that are decaying means that there's many, many, many others that are not decaying. So activity is simply the rate of change. So something that has a shorter half-life will have a much more rapid rate of change versus something that is much longer lived. So looking at the actual equation, activity is equal to the decay constant times the number of atoms you have present. So yeah, that's useful for figuring out the number of atoms present if you have information like the isotope and the activity of the isotope. There's something known as banana equivalent dose. This is essentially just the dose you get from eating a banana, with the underlying thought that, or just the underlying knowledge that a certain percentage of potassium in the world is radioactive potassium. It's K40. It's actually the largest activity of radioactive material in your body. There's a lot of potassium in your body for certain biological functions. So a small percentage of this is radioactive potassium, to the point that you have to calculate for that when you're doing whole body scans and other sort of nuclear medicine procedures. They have to sort of eliminate that background of potassium-40 in order to either visualize or quantify a certain level of other isotope inside of a body. So you tell this to people, and a lot of people get terrified. They're blown away that bananas are radioactive, but it's a very small level of radiation. It's about 0.01 millirem per banana that you eat. So that's next to nothing in terms of just regular background levels of radiation from other sources. There's a little bit of math. It's good to go through the math to figure that out. We'll do that when we're meeting in person because it's a little complicated. So I'll just walk it through step by step, and I could also just show you guys the Excel calculation of it. So this is the actual decay equation. I'm pretty sure you must have gone over this at least briefly in Brian's class. Maybe it's still to be gone over because you guys said you had a week or two left of that class. But it's very useful. It's something we use all day, every day in radiation safety, just to figure out, how long our waste is going to stick around, how long a patient will remain radioactive. There's millions of different uses for knowing when something that is radioactive will no longer be radioactive. So essentially, it's just the equation is your activity for the time that you're looking at. So that AF is your final activity is equal to your A naught, which is that initial activity, times E to the negative lambda T. E is just a value that is common in math for things that are actually multiplying, but because it has a negative exponent, it's for this certain instance, it's useful for decay. So I hope you guys have some experience with the natural log function on a calculator. This will make it a lot easier to calculate these sort of things. But that lambda in this equation turns into the natural log of 2 over the half-life. So in this situation, if you have the isotope in question, you have a half-life, you have your initial activity. So if you're looking for how much activity is present at a certain time, you'll have the T value, and then it's just a matter of plugging in the values and getting your value. One easy place to get tripped up here is that you have to make sure that your half-life and your time of interest is in the same units. It's very easy to have a half-life that's in days, but you're looking for how much decay happened after a year or after a week or after a month. So you have to make sure, down to seconds, minutes, hours, days. You really just have to make sure they are in the same unit, or else you will get an incorrect answer. So when you actually go to solve one of these equations, you really just have to be familiar with the functions on the calculator. If you're solving for final activity, it's pretty straightforward. You just use the E button on your calculator. Make sure you use good parentheses in order to denote, isolate the actual lambda value with the T before you take the exponent of it. Hopefully we can do a couple of examples of this. It's going to be on some homework too, just so you get a little more comfortable with it if you haven't already been shown this equation. Sometimes you're asked to find either a half-life or the time it takes for a certain activity to decay to another activity. And in that case, you need to actually be comfortable sort of manipulating the decay equation. So that's really, it just comes down to algebra. You got to get the A naught, so that initial activity, over to the left side of the equation. And then once you have it over to the left side of the equation, that allows you to take the natural log of both sides. And the natural log of E it's the inverse, so they erase. And that gives you this equation that you see here on the right. That is the equation that you would use for figuring out either half-life or T. Because the equation on the left, it should just be a constant. And in a situation where you're asked to find half-life or find the time it takes to decay to something, you really should have been given both a value for A, F, and A naught. And that would just mean that will just be a number. And then once you have that number, you can either multiply by the half-life or divide through by the time to get the other variable. Again, it's hard to talk through math. It's better just to see it done. So we'll figure out a way, if you guys have some questions about it, we'll figure out a way to just go through a couple of these just to make sure everyone's on the same page. And the last thing when talking about half-life and decay is really everything we talked about so far is physical decay. That's sort of a law of nature. It's set in stone, specific to the isotope. These isotopes decay the same under intense pressures, intense heat. There's no physical environment that we know of that changes this physical decay. It's a law of nature. However, as soon as you put some sort of radioisotope into a biological system, whether it's a patient or a research animal or something like that, there will be some element of biological removal. That so if you're interested in looking at the activity inside of that patient or inside of that research animal, you have to account for that biological removal and the physical decay. And so that's where that you get this equation that shows the effective half-life. And that's simply the product of the two. So just the multiplication of the two over the addition of the two, over the sum of the two. And that's useful in situations like when we're treating patients, we give large doses of radioiodine to thyroid cancer patients, but these patients have almost always had their thyroid removed surgically prior to getting this radioactive iodine. It's for thyroid cancer, so they want to remove the cancer as best they can, and then they do radioablation with the iodine. So the biological element of the biological removal of this therapy is very rapid. We give these patients 250, sometimes 300 millicuries of iodine, and they will pee out 99.5% of it in the first 24 hours. It's really that 0.5% that sticks in the thyroid tissue that is giving the therapeutic benefit. But we know that most of it's going to come out very rapidly. So that's useful for us because that means that when we're talking to these patients about how they spend time around their family safely, they hear, oh, iodine 131 has an 8-day half-life. I'm going to be radioactive for months. But it's no, so much of it is going to leave in that first 24 hours that it'll be such a small percentage of it that sticks. The small percentage that sticks will decay with something closer to the physical half-life. There will still be some removal, but nothing like that first 24, 48-hour period. So it's important to know that if biological decay will play a role in the scenario, the real world scenario you're looking at, and to account for it, if for nothing else, then just, patient comfort, I guess, so that they're not isolated from their family because they think that they're going to be radioactive for months, when in fact they're really only going to be radioactive for the first maybe week after therapy, and after that they really won't be a hazard to anybody. So that's one example. There's tons of examples where you need to have this effective half-life, just to give you a real world idea of what's remaining in a patient. And that's it for radioactive decay. We'll discuss on Thursday.